So I'm Ewan Crespo, as is said. I'm a local guy. I'm currently in a PhD with Guy Casal and Loïc Lemarec at the University of Rennes. So we talk about geometric modeling of microstructural material. So my thesis is at the crossroad of continuous continuum mechanics and differential geometry, and it follows on from a previous thesis by Van Ooy and Nguyen. The aim of this work is to provide a modeling for microstructure mechanical materials, which are materials that can be observed at a microscopic scale, for example, a wooden beam or a crystal, but whose microscopic stage, such as the orientation of the crystals, impact their macroscopic behavior. So this is not new work. It was first introduced by the Kossera brothers from a mechanical point of view, and then by Cartan from a mathematical point of view, and then numerous work through the last century. Okay, so in classical continuum mechanics, there are two scales. There's the macroscopic scale, the length of what you want to measure, for example, the length of the beam, and the nanoscopic scale corresponding to the scale at which fundamentally discrete phenomena appear. So our approach is to enrich this classical model with an intermediary scale, the microscopic scale, okay, and with some negligibility assumptions, we can then see our material as a macroscopic continuum whose points are microscopic continuum, whose points are cluster of nanoscopic points. So we'll forget about the nanoscopic scale, but we'll keep the microscopic scale focus. And so the microscopic over macroscopic length ratio will play a key role in our model. It'll be called the scale factor and noted zeta. Okay, which is less than 1 is small. Okay, so let's name things. So first we have the macroscopic continuum, which is the usual continuum. It can be three-dimensional, but it can be less. Okay, it will be called the base. It will be the base of the fiber bundle, and noted B. Then we have the microscopic space at a point of B, at a point X of B, which will be noted MX, and will be called the fiber. And we have then the disjunct union of the MX, that is called M, which is also called the total space. And we have the application that to a point of M provides the macroscopic point inside of which it resides, which we call the macroscopic projection and not by M. So this provides half of the structure of a fiber bundle, and we make the assumption that it is a fiber bundle, which means that additionally it's homogeneous, meaning that all the microspaces are alike, isomorphic, and locally trivial, meaning that in a way microscopic fibers are touching, macroscopic points are touching. Well, locally it's a Cartesian product. That's a topological assumption. All right. A good illustration for a fiber bundle like we see them would be a navigation tool such as Google Street View, where the base, the macroscopic world, would be the map of the world in 2D, and a fiber, a microspace at the point, would be a 3D panoramic view at that location. Okay, so you imagine fibers inside the microscopic space, microscopic points. Okay, so we'll also need to talk about fiber morphisms, which are applications that maps fibers into fibers. That is, they don't break fibers. So if you have a point at a macroscopic point or a point in the starting base, then the fiber in that point is sent to a fiber at another point in the target base. So that defines an application between the bases that we call the shadow of the morphism, and not with a novel line. Okay, this is equivalent to the commutation of this diagram and the existence of this. All right. So all those definitions, these approaches, and this naming lead to natural interpretation of our objects, which we call the standard interpretation. It basically says three main things. The first one is that every object of a microstructural material should be elements of a fiber bundle. Okay, the second one is that the only thing that one can measure about this object is the projection onto the base of the fiber of the bundle, or the shadow for morphisms, which we call the macroscopic part. And the last one is that those macroscopic parts can be expressed as kinematic objects of the classical continuum mechanics. So everything is in a fiber bundle. We can also only see the macroscopic parts, and those macroscopic parts are the usual stuff of the continuum mechanics. Okay, one of the first consequences of this axiom is that the ambient space is a fiber bundle. But it's not any fiber bundle, because it has no defects. The defects are in the material. So it means that all the microscopic spaces are of the same shape. They will align between themselves and one another, and they will align with the macroscopic world. This turns out to mathematically mean that E, the ambient space fiber bundle, is identifiable with the Euclidean tangent. This can be interpreted as saying that the microscopic space at the point X can be seen as the standard infinitesimal neighborhood of that point. All right, but it's not always the case, especially for the material, which will have defect. And so we need additional tools to measure the misalignment of these microscopic spaces. So we need two tools. The first one can be seen in the interpretation of the Google Street View I gave you just 5 minutes ago. When you're in panoramic view at a location in Google Street View, you can still follow a macroscopic route on a map. You will then see the panorama being continuously transformed into a panorama at an infinitesimally close location. So this map between movements of macroscopic points and movements of the whole fiber is a special kind of map, is called an Ehresmann connection. In our case, on the ambient space, it's the Levi-Civita connection. Okay, we define an Ehresmann connection as a linear injective projection from the tangent of the base, that is a space of macroscopic movements, to the tangent of the total space, that is a space of possible movements of the points on the fibers, such that the macroscopic part of the images is the starting vector. That is, if you induce a movement of the fiber, if you zoom out, then the fiber moves along the macroscopic vector you provided. Okay, so this is not the usual kind of connection we talk about. So in the case where the fibers is linear and the connection is linear on the coordinate of the fiber, which is usually the case in our example, we get a new index for the connection in the coordinate on the fiber. And so we fall back to another kind of of connection, which is the Koszul connection. In our case, this is a Levi-Civita connection, so the gamma ijk are just the Christoffel symbols. Okay, the Koszul connection are also often defined using the covariant derivative operator. In our case, it's simply, at least for section, the microscopic part of the usual derivative, where the microscopic part is, roughly speaking, the complementary of our connection. Right. So the second tool can also be seen in the Google Street View example. It's way more simple. It's just that when you're in a panoramic view, you know where the north is. More generally, you can point toward any direction on the map while being in a panorama. So this defines the map from macroscopic direction to microscopic one, which is a special kind of application too, and it's called a pseudoform. So we choose to define a pseudoform as also a linear injective map from the tangent of the base to the tangent of the total space, but this time we require it to be microscopic, that is, its macroscopic images are, the macroscopic part of the images are 0. All right. So now that we have those two tools on the ambient space, we're going to define first order configuration of material, of fiber bundle. So just a quick warning, pay attention to the dimensions of the space, because they may be conflict. We use F, but it's not the usual F, for example. So this will be summarized in this commutative diagram. Okay, and this illustration of a particular example of transformation, which is not generic at all. Just a quick explanation. This is a 4-dimensional space, so we chose to represent the macroscopic space as discretized blue points, okay? And the microscopic space at a point, a blue point, is represented as a flat infinitesimal pink neighborhood. So everything is flattened out, but it's supposed to be a 4-dimensional space, okay? And the blue point is supposed to be continuous, of course. Okay, so the first application we have is the punctual configuration. This is an injective map from M to E. In our example, it's 4-dimensional. Okay, and the standard interpretation then promptly dictates that it must be a fiber bundle morphism, and that its shadow must be the usual macroscopic configuration. So this is this part of the commutative diagram. Okay, then we have the first order configuration, which is a map from the tangent of the macroscopic total space to the tangent of the ambient total space, which is by construction maps a vector at x to a vector at phi of x. Okay, so this means that it's a fiber bundle for the punctual projection. Okay, this is this commutative diagram here, and that its shadow is phi. But the standard interpretation dictates that f must be a fiber bundle for the macroscopic projection, and that its shadow should be the usual macroscopic first order configuration, which is, as you probably know, the gradient of the macroscopic punctual projection. So this leads to this other half of the gradient. So there's two things you need to notice here. Well, there's the dimension, because this is not a 3x3 matrix, but it's a 4x4 matrix or even higher. And then there's the fact that f does not have to be a gradient, and phi does not have to transform the macroscopic space and the microscopic space the same way as is illustrated here. As you can see, the microspace is rotated while the points are not. Okay. This is simply because the standard interpretation does not imply it. But if you fix that, and you notice that M can be identified with the gradient of B, then it turns out that it kills any torsion, curvature, or deflectances, and you just fall back to the classical continuum mechanics. You just differentiate twice. Okay. So we want to assume that. Okay, so now that we have the configuration, we can use it to pull back our solder form and our connection on the material space. So this is done the usual way. So we superimpose M over E. And so we have the microscopic space, the microscopic vector in the material space. We use the first order macroscopic transformation to superimpose it on E. Then we do our stuff in E. And then we use F to superimpose it back onto the material total tangent space. Okay, this is the usual pullback operation, but it's... So we get gamma, the big gamma and the big theta, which are on the material space. Right. So as a more in-depth example, we choose to talk about the beam model. So I said it quickly earlier, but we assume some injectivity that fix the dimensions. So the microspaces have to be 3-dimensional, okay, but the macroscopic space does not. In fact, it can be less, and we use this fact to define a beam as the 1x3 fiber bundle. That is, fibers can be seen as thin slices of the beam, and the macroscopic space can be identified with a real interval, closed interval. Okay, and from the one-dimensionality of the macroscopic space, this means that the solder form can be seen as a vector space, a vector field, pointing toward the direction of the beam. And the connection can be seen as a vector field also, but this time indicating how adjacent slices are positioned one relative to another. Okay, so this is a bit simpler. As it turns out, our connection, our solder form, are nearly enough to define usual beam theory measures of deformation. Okay, the last one seems maybe a bit threatening, but it's just a microscopic Cauchy-Green, just a metric on the microspaces. All right, and so if we use them, we can then redefine the usual model by restricting our transformation. So the first model is the Timoshenko LSS model, which requires rigidity of the slices and the lack of disclinations. If we do that, and if we split heuristically the space as macro and micro, then we can split F as a block matrix. And we then realize that because of the slice rigidity, the micro to micro part is constant up to rotation. Okay, so there is a conjugation with the solid form, but we can ignore that. The second model is the Euler-Bernoulli E1, where we define this second measure of deformation to be 0, constant, and then it turns out that the macro to macro space is also constant, up to the same rotation as the microspace. And as for example, we have the rigid bar where we set the last measure of deformation to be constant, and then we don't have anything less. It turns out that this term, this cross term becomes 0, okay, and the rotation becomes constant. So we just have the bar that rotates but doesn't bend. All right. So the beam has nothing special. We can also retrieve the Errington measure of deformation in his microcontinuum field theory, which is a 3x3 fiber bundle. And just as for the beam model, we don't have to assume what we do if you want to retrieve Errington, but we can generalize it to the case where F is not a gradient. So there would be dislocations, and the case where the macroscopic space is not three-dimensional in the case of Errington. Okay. All in all, we have seen that we have constructed a model that is very general, that can be reduced to a lot of other models because we skip some, and with allowing for generalization. Thank you for listening.
In your applications, your connection is free torsion or not?
It's in general, it's not the microphone. Sorry. In general, it's not. It can be. It can have torsion. In the case, I've tried to reduce to the usual beam model, which has no defects, so it probably doesn't have any torsion. But in general, it can have torsion and can have curvature also if we do not force F to be the gradient. And there has been some example by the previous thesis where there are explicit construction, explicit transformation, where there is torsion and there is a curvature tensor that is not null.
To explain plasticity from the dislocation movement, it is included in your framework?
We hope to, but we haven't gone to that part yet. But of course, one of the next step is to have some energy or things like that, and we hope to be able to explain plasticity with these defects that appears from the fact that the micro and the macro space do not transform the same way. So, for example, you see kind of a micro rotation defect here that could explain my plasticity. But yeah, we probably make some link with usual already existing works about it. I'm doing all the work.
Thank you. Just a question. You include this connection as an extra data in the problem, because in principle you don't need the connection just to develop the theory, because you only need to consider the one jets or the gradients of the local isomorphism original medium with microstructure into the model. So this is an extra assumption.
When you reduce to the F
Yeah.
is a gradient case.
Yes.
Yeah, well, our objective is not to do again the beam model. It's just to motivate that we still have the capacity to have such model. But of course, this assumption we do not want at all. That's where the interesting stuff appears. But it's true that if you have F as a gradient, then there's no need for all this connection and soliform stuff. But this last part was just a motivation to show you that it's not a different model. It's a more general model that includes the previous one. Okay, so you can easily add defects to beams. I mean, easily in a kinematic way. I don't know about the energy bit.
For example, for Coursera media, the bundle is just the frame bundle of the macro medium, and you have to take the gradients of the one jets of the local isomorphism from this the frame bundle of the macro body into the frame bundle of R3, because R3 will be the ambient physical space, and you don't need a connection to develop a theory of just to consider uniformity or homogeneity or these things. Coursera is just you have the three vector attached to any point at the macro medium, and so you the idea is just to look the deformation of this triad of vectors along the deformation of the body. So we have two deformations: the deformation in the macro medium and the deformation in the fiber. And in this case, you have a Lie group acting on the fiber, so you can do this. You don't need to consider all the derivatives along all the points of the fiber, just in one point, because you have the homogeneity given by the action of the Lie group. That's just.
Oh yeah, no, it's a good comment. I thought.
Every slice belongs to basic theory.
Yeah, I know. We can actually. Well, we haven't done the work, but we think that it's very likely that we can go back to Coursera medium by just doing a quotient of our space under the action of the group, and then we fall back to the principal bundle, and the configuration goes to the quotient, and everything goes to the quotient, and we have a transformation where instead of having 3 points transformation, 3x3 matrix, you just have an angle, which is actually in the paper it's mentioned. But yeah, I thought in the Coursera they didn't use F as 2.5, but maybe you may be right. I'll check it.
Coursera is the most general. So
Yeah, but I've written it somewhere in the future goal. Yeah, here.
The interesting idea is that the idea of the Coursera process is just the same as the idea of Lie Cartan to define connectors in principal numbers. It's just the same idea.
it was a very interesting talk. Thank you very much.